Hi, this is Nathan. The next example I want to do on MLEs is the Poisson distribution. Poisson. Spelling is not my strong suit. So the PMF for each one of these is e to negative lambda to the xi over xi factorial. So the joint PMF which is equal to the likelihood function is equal to the sum from I equals 1 to n, because we have n samples, times e to negative lambda to the xi over xi factorial, or the log likelihood function. It's the sum of the log of each PMF, which is equal to, if you distribute in the log, it's the sum of ln of e to negative lambda plus ln of lambda to the xi, should add parentheses, minus, because it's in the denominator, ln of xi factorial, which is equal to, just going to simplify these logarithms, sum of negative lambda log of e is 1, so that's it, plus xi times the log of lambda minus ln of xi factorial. Can't do much with this one, but that's okay, because when we take the derivative with respect to lambda, because that's the parameter, this is going to get us sum of negative 1 plus xi over lambda. Now this doesn't have any lambdas in it, right? So that's going to just have a derivative of 0 when we take the derivative with respect to lambda. That's why it didn't really matter how ugly the factorial term looks. Now I'm going to distribute in this sum, and this gets us negative n plus sum of xi over lambda, and we're setting it equal to 0, right? So if you move the n over, we get sum of xi over lambda is equal to n, or if you swap the lambda and n, we get lambda hat MLE is equal to sum of xi over n. Again, just as how it's been on the other examples, lambda is equal to the expected value of this distribution, right? So it makes sense that lambda hat is going to be equal to the sample mean. Now I want to use this fairly simple example to highlight something that I've kind of been skimming over so far. When you find the maximum of a function, it isn't quite as simple as just taking the derivative and setting it equal to 0, right? That just lets us know that what we have is one of the critical points. So to verify that it's actually the maximum, what we can do is find the second derivative and make sure that it's less than 0. Because if the second derivative is less than 0, then we know that the function will look like this because the slope is going to be decreasing, and at this point that we found, this critical point, is a maximum. Okay, so let's do this for the Poisson distribution. We have the log likelihood function, L of lambda. We have, just writing this from right here, sum of negative lambda plus xi times the log of lambda minus log of xi factorial, right? Now we want the second derivative of this, which is equal to the derivative of the derivative of the function, right? And we know the derivative of this function is this, so that gets us the derivative of sum of negative 1 plus xi over lambda, or distributing in this summation, we get the derivative of negative n plus sum of xi over lambda, right? Now, let's take this derivative. This term has no lambda, so that's going to be 0. This term will get us sum of xi over lambda squared, except it's negative, because that's what the derivative is. Now, what do we know about the Poisson distribution? We know that x1, xn are all greater than or equal to 0, right? And that lambda has to be greater than 0. The parameter has to be a number greater than 0. So we know the denominator is greater than 0. We knew the numerator with the negative sign is the sum of non-negative integers. So that's going to get us that this is less than 0. And so we have a negative number over a positive number, which is going to get us a negative number for the second derivative for all values of lambda, right? So if we draw, this is lambda, this is log likelihood of lambda, it's going to look something like this, where this is the maximum likelihood estimator that we found, because the second derivative is less than 0 for all, I guess lambda can't be less than 0, so ignore this.